All right, good morning, folks. Happy Monday. I'm going to go ahead and start with a few announcements. So I just posted this week's announcements. So we'll take a look at that on Canvas, and then we will jump into 6.8, finish that up, and then see what other kinds of questions we have for today. Okay. All right, so here are the announcements for this week. Okay, so we are in week 6 of class. So we have this week, we have next week, and then we have one more week. All right, you folks are kind of in I think the toughest time. We're sort of at that 2/3 mark where we're a little bit more than halfway, but we're still not quite close enough to the finish line. And I think this is a great time to kind of dig in and really think, okay, what can I accomplish in the next week? And as far as our schedule, here's what we have. So today we're going to finish 6.8 based off of the pretty universal feedback that it would be better to keep the exam day the way it is and just have less content. This exam will go up through and including 6.8, but it will not cover, as it was originally intended, 19.1 and 7.6. Okay, so today's content is on the exam that you will have tomorrow. Tomorrow we will not meet as a class, but you'll have time to work on your exam. Now, please remember that it is a little bit different and that you have sort of one time frame to sit and work on that. And then on Wednesday, we're going to finish this unit. So we're sort of splitting it a little bit, but we're going to cover 19.1 and 7.6 on Wednesday. And that sort of day's work is really going to be like an appetizer for differential equations, just to kind of see like, all right, this whole course, like the highest math course they offer at Mesa, what's it all about? We're going to kind of get a very brief introduction to it on Wednesday, okay? And then on Thursday, we are going to begin chapter 11. And for better or for worse, this is our final chapter for the summer, okay? So we have covered all of the stuff that is going to be really important for Calc 3. We've made sure to cover that in the beginning, so we don't have to worry about, missing some topics or not feeling prepared for the immediate next class. And chapter 11, it's a really interesting chapter. We'll get through as much as we can get through because it's definitely content that comes up again, but maybe not until a little bit later in your math careers, okay? Quiz 10 is due tomorrow by 9:30. I will post an answer key as that content is going to be on the exam. So I want to make sure that you have an answer key to compare your answers to before you submit your quiz. Okay, so be on the lookout for that. I'll probably post that in the very early afternoon. So there should be a key for you to check quiz 10 with and hopefully help you just tidy up that last bit of studying that you might have. Quiz 11 is going to be due on Friday morning at 9:30, but it's only going to cover 19.1 and 7.6. Okay, so it should be a little bit of a shorter quiz that you could start as early as Wednesday and also be done as early as Wednesday. I know it's always tough on exam weeks to have like the quizzes and the tests, so I tried to make that second quiz a little bit lighter, okay? Other than that, the rundown of the exams for the rest of the semester. So on Tuesday, let me change that. On Tuesday, we have exam 3, and it is only covering those sections, all right? So exam 4 will be covering 19.1, 7.6, and probably 11.1 through 11.5, 4 or 5, but I'll come back and modify that before we get to that exam. Your final exam will be on Thursday, August 6th. So we've got 3 weeks left, 3 exams. I know that's a lot, but again, just kind of dig those heels in there. I know you got this. Even if you're tired, I know that you can push through because you've already come so far. So keep it up to the end of the semester, okay? Are there any questions on the announcements?
Has the schedule been updated on the website?
It should be. I've been updating it kind of as we go.
Will we have time at the end of lecture today to, I just had a quick question about the cheat sheet.
Yeah, I think so. I think so.
Okay. I'll hold it till the end of lecture then.
Okay, cool. Any other questions? When is the last official day of summer or summer school? I don't know the last official day for summer, but I know summer school for you folks should end. Our last day is Thursday the 6th. Okay, so not this Thursday, not next Thursday, but the Thursday after that. All right, and this is a quick turnaround, but if you are taking MESA classes or City or Miramar classes, our fall semester begins Monday, August 17th. Okay. All right. Well then, let's go ahead and get started. I don't think that 6.8 will take the whole time, but again, it's a really conceptual one in terms of the setup, kind of like a lot of the applications. So do ask questions. Do feel free to interrupt. We don't really have as quite as tight of a time frame today as maybe we had last week. Okay.
I have one question before you start, if that's okay.
Mm-hmm.
You know how the first question is writing the integrity thing? Well, we have to, cause like we have to do 1 and then 2. Normally, you know how we put that on top of our cheat sheet. Can we do? Are we gonna be able to do it separately to where we have one whole page to just do the cheat sheet?
They're separate questions.
Great. Okay,
Yeah.
thank you.
Yeah, and that's a great reminder. So in preparation for tomorrow, it might be a good idea to save some time. You can, one, prep your statement of integrity. So what I mean is write that out, sign it tonight, okay? Write it in your own handwriting and sign it. Some folks like to write it but not sign it. Some folks like to sign it but not write it. So do both of those, okay? So I would do that tonight, just so that whenever you start your exam, you're ready to go. The statement will not change, except for maybe if you, well, let me just double check, but maybe I can post that so you can prep that tonight. And the other thing is I would prep that cheat sheet in advance, so you have all that ready to go. I know that a few folks are still a little nervous about the uploading time. And again, I would, if you have any kind of smartphone, it doesn't have to be an iPhone. You can take photos on your phone, and there are apps that will turn it into a PDF for you. So it shouldn't take more than a couple minutes to take the photo and upload it. I know sometimes some internet is slower than others, but it shouldn't take, it shouldn't be quite such a long process. Okay, there are ways around that, even if you don't have the fanciest, latest, up-to-date phone. Are we using calculators on the test? There are going to be some questions where you have calculator, and by calculator I mean scientific calculator. And there are questions, there are some questions that I'll stay like, leave your answer in exact form. So just make sure to read those directions carefully, okay? That would be awesome, Alina. Yeah, so if anybody might have a question on how to upload things, Alina here has offered to maybe help folks out. So be in contact with her, send her a message through the chat, and maybe you guys can work that out. Thank you so much for that. Okay, any other questions, folks, before we jump into our fluid force? All right. All righty, so okay. Ah, yes, my terrible drawings from Thursday. Okay. It was kind of embarrassing. Like, these things are all fun and good while you're like in a classroom and you're drawing, you know, pictures that are not very artistic, and it's sort of like between you and your students. But then when you post them on the internet, it's sort of a whole nother story, because now I'm sure there are other people judging the quality of my stick figures. But here we are. So on Thursday, we started fluid forces, and we talked a little bit about how if you've ever been in a body of water, swimming, or, you know, just soaking in a tub or whatnot, that the closer you are to the surface, the less pressure there is, and the further down below the surface you are, the more pressure there is. And so we're taking that idea to talk about the force of fluid on a plate. And so I know we're talking very generally about some random plate submerged in water, but the actual applications of this are, if you've ever seen a dam, like, you know, when they have like a whole body of water, and then they like put a plate basically in front of the water so it can't escape, and sort of it's in this reservoir, and there's a lot of pressure on that wall. And so when engineers are designing the structures for the dam, they need to consider that the forces on the bottom of that wall are going to be different than the forces closer to the top. And if they want this dam to hold up, they need to make sure that the structure incorporates extra strength on the bottom and maybe less strength on the top, right? Because they don't want to make the whole thing extra. It's really about like minimizing the cost, but also maximizing the structural integrity of whatever they are designing. Okay, so this happens a lot in structural engineering, where you have to include that idea of fluid and force as it changes across the depth. And so we spent a lot of time on this one question here, where we had a triangular plate, all right? We were given some measurements, and then we found this formula. Okay, so let's maybe put a box around this formula. So this formula right here, okay, this is really where we are going to be starting for all of the questions. Okay, so we're going to start with like filling in our density, our gravity, our depth, and our area. So like all of this stuff. Okay, everything above that bigger pink bubble is really just like the conceptual setup. Okay, so thinking about where this formula comes from, why is it structured the way it is, and how might it change given different shapes of plates that we have. So like in this case, we have a triangle, but we're gonna take a look at some squares, some trapezoids, as well as circular shapes, okay? So we took the idea of finding the force of a single slice and extended it to the force of a whole plate with the integral, okay? And so we, at the end, we had our integral, where we were looking at the density and the gravity, but the depth, this 3 plus y, we're going to talk more about where that comes from today and how that applies to different ones. And then for this part right here, we had to use the idea of similar triangles to find the equation. okay? And that's not always going to be true. Like we won't always use similar triangles, but sometimes we do. Usually in a case like this, we do not need to use it for a square. We do not need to use it for a circle, but we might draw upon this for the trapezoid, okay? So don't think about, oh, every single time I have to use similar triangles. Sometimes you do if you see sort of a triangular shape, and sometimes you don't if you see like sort of a round shape or a rectangular shape. Okay. Now, before we take a look at example number 2, were there any questions about where we left off with fluid force on Thursday? Okay. So let's jump in then and let's take a look at example number 2, okay? So this one says, find the hydrostatic force against a 4x4 square plate submerged underwater so that the center is 10 feet under the surface of the water, okay? Now, just to kind of think about where we're going to be going, you'll notice that we have a setup number 1, setup number 2, and setup number 3, okay? Now, all 3 setups will give us the same answer, and we're not going to integrate every single one. But I do want to talk about how you can kind of choose what makes more sense to you for your setup, okay? It is going to be different for everyone. Like everyone's got a different way of looking at it. So maybe just kind of think about which one works better for you and which one might feel that you might feel comfortable using tomorrow. Okay. All right. So regardless, we're going to start off with a diagram. Okay. So we've got this surface of the water. And we've got a plate that is a square plate, okay? Okay. Now this square plate, we know that the center of it is 10 feet under the surface of the water. So I know from here to halfway down is 10 feet, okay? I also know that this is 4 feet and this is also 4 feet, right? Now, the way that we are going to start is we're going to write out force. We're going to talk about the different parts of the force equation, and then we're going to talk about the equation that goes into our integral, okay? So we know from last week that force equals pressure times the area, okay? And we also said on Thursday that we could say that pressure is really density times the depth, because again, it changes according to the depth, and times the area. Okay, so the area is going to change from, like, this area is going to be different than our previous area in the sense that, like, this shape is a square and the other one was a triangle, okay? But one thing that doesn't really change is if we take the idea of taking a specific slice, okay? So last time we drew a random slice, this time we're drawing a random slice. That random slice is what's going to contribute to our area formula, okay? So the area formula is still going to be assuming that we have a very thin rectangle, and that doesn't change, all right? So if we were to expand this, if we were to expand this, we've got density times depth times the width and the thickness, right? Because the width and the thickness, that makes our area, okay? Width and thickness are what make up the area. Now, in this case, we have our plate, and the plate is submerged in water, okay? So when we're looking with feet and pounds, the density of water is a constant, and it is 62.5, okay? So that density, if it's water and we're dealing with feet, will be 62.5. Now that's a different number from on Thursday because we weren't looking at it with feet. We were measuring it with different units, okay? Now I believe the problems tomorrow are all with feet. So 62.5 is a good number to know for the density of water, right? So we've got our density. Okay. Now, in terms of depth, here's how I'm going to do the first setup. This is something that kind of makes sense to me, but if you look after we go through setup number 1, if you're like just hold some questions and see if setup 2 or 3 make more sense to you, okay? This is just how I happen to see it, but again, it might not be what comes most easily to other folks, okay? So if I think about my axes, I took my axes to be here at the top of the square, and then halfway down, all right? So I sort of considered this my X and this my Y. That means that when I'm looking at my depth, I know that the smallest depth I can have is from the surface of the water to the top of the square. How far is that distance?
8 feet.
Yeah, it's 8 feet. How did you get 8 feet?
Half of 4 is from the center to the top, and you minus that from the depth of the center to the top.
Yeah, so I know that it's 10 from the surface to the center, but I only want from the surface to the top of the square. So the difference is 2, so 10 minus 2 gives me 8. Okay. Now 8 is the smallest depth that it can be, but that depth only gets larger as I go down under the water. Like the bottom of the plate has a greater distance to the surface of the water. So I actually take my XY, like instead of a positive Y being up, I actually kind of make it facing down so that it's in the direction that the depth is changing. So to my 8, I add Y, because that will get me the extra distance of the square. Okay, so the depth here is 8 plus Y. Now, what is the width of each rectangular slice that I take? Does it change or is it constant?
Constant.
Constant.
Constant, yeah. And what is that width?
4.
It is 4, very good. So my width, I'm going to have 4, and that is my width. And my thickness, because I'm stacking these rectangles along the y-axis, is just dy. Okay. So this 4 dy at the end takes care of the area of a single slice along my 4 by 4 square plate. Okay. So now let's set up our integral. All right, so we've got force equals the integral of 62.5 times 8 plus y times 4 dy. Right? So like everything I did above was really a setup, so I knew like what my integral is going to be. What are my bounds going to be given the way my coordinate axes are set up?
12, 8 to 12.
0 to 4.
0 to 2.
All right, I hear a few different answers here. So if we start right here, right, and we consider that to be the top of the plate, that's where we want to start looking at the fluid force. So what's the y value there?
8.
Not according to the way that I set up my coordinate axes.
0.
Yeah, it's going to be 0, right? It's right along the x-axis. Now, if I travel down to the bottom of the plate, how far have I gone?
4.
Gone 4 units, right? So I'm going to go from 0 to 4 for my integral, okay? Because I don't want to just go halfway. I want to go all the way from the top of the plate to the bottom of the plate. Okay. I think everything that we've done so far is actually the hardest part. Okay, the diagram, the setup, having the bounds for our integral. But after this, we just need to integrate, and it's actually a very simple integral, okay? So what I'm going to do first, I'm going to take my constants out to the front. So I'm going to take the 62.5 and the 4. I'm going to move those to the front, and that'll give me 250 as my constant. The integral from 0 to 4 of 8 plus y dy. Okay. And so when we integrate, we've got 250 times 8y plus y squared over 2, plugging in 4, plugging in 0. And so that will give us 250 times 4 times 8 is 32, plus 16 over 2 is 8, and then minus 0, because when I plug in 0, everything goes away in my integral. And so I end up with 250 times 40, or 10,000 foot-pounds. Okay. So again, this is one way that we can set up our problem, but at the end, our integrals are usually way less complex than anything we saw in chapter 9. So we're not looking for like partial fractions, trig sub, maybe a u sub here or there, but mostly just straight up power rule and power rule with whole numbers. There's not even negative numbers, okay? So when you are studying, I would really encourage you to focus on the diagram, the equation setup, and the bounds. Like make sure those are good, because I trust you guys to integrate an expression like this. So I hope you trust yourself to do that, because I know that based off of what I've seen, we can all integrate like this. The bigger question is, can we set it up so that we get that right answer? Okay. So let's take a look at maybe a different way that I could have drawn my diagram, and based off of that, how that impacts our actual integral and how it impacts our answer. Okay. All right. So setup number 2. I'm going to have the surface of my water. I'm going to have my square plate. Okay. And when I think about drawing the coordinate axes, I'm still going to split, like I'm going to keep my y-axis right down the middle of my plate, okay? Having the y-axis as the middle of the plate is generally a pretty good idea, because what you're doing is you're embracing the symmetry of your shape, all right? And then you're able to use an equation to write what's happening as far as the width goes, all right? But last time when I drew my x-axis, I put it at the top of my square. And this time I'm going to put the x-axis at the bottom of the square, okay? So instead of an x-axis at the top, I'm going to have my x-axis at the bottom of the square. Now, if I set up my integral, I know I need to have my density. That part doesn't change. I know I need to have the depth. I know I have the 4 and the dy. So like that part doesn't change just because I changed my diagram, okay? If I start with my x-axis down here, what's my bottom bound going to be?
Negative
12
4.
or 0?
Yeah, the bottom bound's going to be 0. And then what's my top bound going to be?
Still 4?
It's still going to be 4. Okay, so I'm going from 0 to 4.
You already have how experience with all your little ones. I can see it now.
All right, so now the last thing we have to figure out is the depth. Okay, so with the depth in this case, what is the largest depth that we need to consider the fluid forces for?
12 feet?
12 feet, okay. And we got that because it's 10 from the surface, to the middle. And then we have this other 2, right? So 10 and 2 make 12. Like the bottom of the plate is 12 units from the surface of the water. Now that is the most pressure, the lowest depth. If I want to get any depth for the rest of the plate, I need to do 12 minus y, okay? Because this, if I do 12 minus 0, that gets me 12, which is the very bottom of the plate. But if I wanted only to go to the top of the plate, I would get 8 because it's 12 minus 4. Okay, so we generalize that by saying 12 minus y. Okay, so some things in this changed and some things stayed the same. But if you integrate this on your own time, you should still get the same answer, okay? All right, let's take a look at another way that this question could be set up, all right? So we've got our same surface of the water. We've got our square. And this time, I am going to keep my vertical y-axis that kind of splits it down the middle. But instead of having the x-axis on the bottom of the square or on the top of the square, I'm going to choose the middle of the square. Okay? And so what that means is that this distance right here is 10. Right? Because they said earlier that the center of the square is 10 feet underneath the surface of the water. And so we're just having our axis reflect the question, which is put your axis where they say the center is, okay? But you don't have to choose the center, all right? If you did though, let's see what changes. So I have my integral. Density, does that change? No, so we still have a 62.5 for that density, okay? The depth, that is going to change. So let's leave that blank for right now, okay? What about the width of the slice, any slice that I take?
Same.
Still gonna be 4, good. And I still need a dy because that reflects the distance or the thickness of each yellow slice that I take, okay? All right, so based off of what we've seen so far, what do we think we should put in for our distance?
10 minus y. Maybe.
Why do we have 10 minus y? You're correct.
Because the x starts off at 2. I mean, well, yeah, it's like on 2, but then again, from the top of the surface to the x is 10.
Exactly. Yeah. For the same reason before we put that it was 12 minus y, because we went all the way to the axis, right? Now, our last things that we need to figure out here are our bounds. So what do we think our bounds are for this setup number 3?
-2, +2.
Beautiful. I love it. -2, because we go 2 below to get to that bottom of the plate. And +2 because we go 2 above to get to the top of the plate, okay? And I'll leave you to do this on your own time if you would like, but when you integrate, you should still end up with the same answer, okay? So answers are the same, integrals not that challenging, but knowing the setup, that part is definitely where the work is, okay? All right, so before we move on, here's the whole question on one page, all right? So let's see if there are any questions on this one before we move on.
Yeah, I actually had a question on this one. For the width, you're using that value of 4.
Yeah.
But isn't that value in terms of x, but we're taking the integral of dy, so shouldn't that value be in terms of y?
It is, but what's the width of each slice? The width is an x component.
It's an x, yeah, but we're taking the integral of dy, so shouldn't we find the ratio of x to y?
But it's always constant, right? Like it's always gonna be 4.
Okay.
All right, so like wherever the slice is in this particular case, it doesn't matter, like the width of that yellow slice will always be 4.
Okay, yeah, that makes sense. Thanks.
All right, I saw a couple questions in the chat. Found the depth in number 1. Okay, so the depth in number 1. So when we're looking at the depth in number 1, okay, because I sort of flipped my x and y axis, like I made the top of the y axis, the positive y direction, I made that go down. That's why I labeled this y here. So if I think about the smallest distance I have from the surface to the top, that is 8. And any slice below that, which is anything on the plate, I will have to add more y value to get that depth. Does that clarify the setup for number 1? Okay. And then as far as gravity, because we're working in these feet and pounds, it's actually already taken care of. Okay, so we don't need to worry about gravity because it's already been taken care of in the other constants that we used here. Okay. All right, so let's take a look at maybe where the width is not constant, and that might maybe clarify the situation for you a little bit more. Kyle, I think, is who asked. Okay. All right. So we have this question. The ends of a water trough 8 feet long have the shape of isosceles trapezoids of lower base 4 feet, upper base 6 feet, and altitude 4 feet. So as soon as I've seen these units, I know I'm only going to need to use gravity, or only need to use density of water, the 62.5, and that the gravity is already accounted for in the other units that we're using. Okay. So the question says, find the total force on one end if the trough is full of water. And so we are going to start by drawing a diagram. We're going to draw a diagram of the end of the trough, not of the whole trough. Okay. So what I mean by that is we're going to have a isosceles trapezoid. Now I need to draw this carefully because it says that the lower base is 4 feet and the upper base is 6 feet. So I want to make the top of my trapezoid bigger than the bottom of the trapezoid, which I know is kind of backwards for us, but make sure that your diagram is accurate to the description, okay? So I've got this, which is the top of the trough. I've got the bottom of the trough. And then it's an isosceles trapezoid. That means that the two side pieces are the same length. So from here to here is the same as from here to here. Okay. Now we're going to set up a coordinate axis for this, okay? And again, you can kind of go with whatever axis makes sense to you, all right, which may or may not be the same as the way that I'm setting things up, all right? But I am going to, and I hope we all do this, keep the y-axis to be vertical down the center of my shape. So I have a y-axis that is here, okay? And in this particular question, I'm going to go ahead and put the x-axis along the top. Although for some of you, you may want to try putting it on the bottom, okay? And then because I know that it's not a constant width the whole time, like every yellow slice that I take, like this yellow slice will have a different width than this yellow slice. And so because it's not constant, I can't just put a number in there. I have to put an equation like I did, for example, number 1, okay? So because I know I'm going to need an equation, I'm going to start to label some coordinates, all right? So for example, if I know that the upper base is 6 feet, what are the coordinates of those 2 points?
-3 and 3.
-3 and 3.
Right? Okay. Now, if we want to think about these bottom 2 points, what are those coordinates?
-2 and 2.
Give me the coordinate, like an x and a y.
-2 is 0 and there's -2 and, well, actually, for the y.
Do -4, -2, -4.
Yeah, where'd you get that -4 from?
When you start at the x-axis, you have to go down 4 feet.
Yeah, exactly. That altitude being 4 means that the lower base is 4 feet below the upper base, okay? All right, so we've got a few coordinates here, and we've got some sample slices, and all of those coordinates take into account the measurements that we were already originally given, okay? So let's do this. Let's set up our force. We know that force is pressure times area. We know that that can be broken down into density times depth times width times dy, or whatever thickness we're looking at. Now, because this trough is full of water and we're looking at feet, I know my density is nothing more than 62.5. Okay. All right, what do we have for our depth here?
Y plus, or 4 minus, Y minus 4. 4 minus Y, sorry.
Why is it 4 minus y?
Would it be 4 plus y since we're going down?
I feel like it has to have an x and a y in the equation because it's going down, but then again, it's getting smaller on the x-axis.
Okay. So if we wanted to find the smallest depth, I think we would all agree that would be at the top of the trough, right? That's like right at the top. What's the equation for that line?
Y plus,
I equals 0.
Yeah, the x-axis is just y equals 0. And when I go down from here, let's think back to our top minus bottom from like when we did area in integrals. So the top curve is 0. The bottom, we're taking away a given y value. So 0 minus y will actually give us our depth for this setup, okay? If you had that x-axis at the bottom though, you could just keep it as y instead of 0 minus y because you'd be going up from the bottom. All right, as far as the width goes, we need to make sure that we write an equation for this, okay? So one of the skills that we've kind of learned so far is this point slope formula being a really easy way to write an equation for a line as long as we have one point and we can count the slope, okay? So the line that I'd like us to find the equation for is this line right here. So what is one point that is on that line?
3, 0.
3, 0. Okay, so I'm going to do x minus 3 and y minus 0. Now you could pick 2, negative 4, and you would still get the same answer, but I think a 3 and a 0, one of those numbers is going to drop out, so it makes a little bit more simpler when we're trying to simplify the equation. All right. Now, what is the slope of this pink line?
4.
It is 4, yeah. 4, a rise of 4, and a run of 1, okay? Now, what that means is we have y equals 4x minus 12 as our equation. But Kyle, as you pointed out earlier, and you are correct, since we have a dy, we need to account for this width in terms of like as x equals something, all right? And so when we solve for x, we will get y plus 12 divided by 4. This represents this part of the width of any slice. Okay, so x equals y plus 12 over 4 represents that horizontal pink line that we have there. So if I want to have the whole width, though, I need to double that so that I get not just the right half of the trough, but I also get the left half of the trough. Right. How we doing so far?
So that only represents half of the slice.
Well, because I put a 2 in there, that now takes care of the other half.
Okay.
Like, this 2 now means that we're looking at that whole thing.
Right. Okay.
All right. Now let's set up our integral and think about our bounds. So force equals the integral. I know I keep my 62.5. I know that I have a negative y. 0 minus y gives me negative y. I'm going to take this 2 and this 4 and bump them out into the front. So I'll have 2 over 4. And then I have y plus 12 left. As far as my bounds go, what is the lowest depth according to the way I have set up the coordinate axes?
-4.
Yes, -4. And the highest depth?
0.
0. There you go. Okay.
I have a question actually.
Yeah, Sean, what's up?
So on this diagram that we drew, we have our bounds from 0 to -4, or from -4 to 0.
Mhm.
On the previous example, I noticed it was like the same setup, like our x and y axis, but it was from 0 to 4. I thought looking at it would be from -4 to 0 on that one too.
Yeah. And so it depends. So the difference here is that I didn't make the bottom, like the y-axis pointing down. I kept that as negative. I didn't change it to positive.
Oh, okay.
Okay.
Yeah, that makes sense.
One of the weird things though is like the orientation here gives me -4 to 0, and that kind of gets taken care of because I have a negative y in there.
Mm-hmm.
Whereas the other one, I just had a positive number. Like it was 8 plus the y, right? So I
Right.
flipped the
Okay.
whole axis in number 1 or number 2, but in this one, I'm still keeping like up as positive, down as negative.
Right. Okay, that makes sense. Thank you.
Can I ask you a question?
Yes.
So when we are submerging things underwater, the top of the water is basically going to be like your real 0. Whereas when we're having tanks and things that are filled with water, the actual bottom of the tank is where our actual zeros are going to be. If that made sense. Because you know how when it was submerged underwater, the top of the water, you would read positive numbers as you go down. But here, if you put the x-axis on the very bottom and you go move up, then you're reading positive numbers?
Yes.
Okay.
Yeah. So if you wanted to set it up with your axes on the bottom, you were more than welcome to do that. Like move that x-axis to the bottom is absolutely fine. Your bounds will change, but your answer at the end should still be the same.
Okay, so only in water is it where like the y-axis is like kind of turned upside down and you're reading positive as you're going down.
I
Sort
mean,
of.
you kind of have flexibility around that. Like I could have made this to be 2 comma positive 4 and just sort of flipped everything as well.
Yeah.
So there's definitely more than one way to approach these. Okay. All right. Well, the good news is the actual integration here is not so bad, right? So we're going to take this 1/2 in the front. I'm also going to bring out the 62.5. So I'll end up with 31.25 as my constant in the front. I'm integrating from -4 to 0 of -y squared minus 12y dy. And this is going to give me 31.25 -y cubed over 3 minus 6y squared. And I'm plugging in 0 and then -4. Okay. And so that is going to give me 31.25. We're going to have 0 when I plug in 0 minus. Plug in a -4, that'll give me 64 over 3. And then minus 6 times 16 will give me 96. Now, there's a couple negative signs I need to be careful of. But the inside fraction should become 224 over 3, I believe. And when you multiply that out, you should get 7,000 over 3 pounds of force along that trapezoidal end of the trough. Okay.
I have a question.
Yes, what's up?
Why here the final answer only has pound without the feet?
When we're looking at the force for, oh yeah, it should be some pounds, sorry. All right, any other questions about example number 3? Yeah.
So if you could, I don't know, I feel like if a question like this comes up on the test, I feel like I'm going to mess up my bounds. By looking at it, what's a good way to, like after we create our diagram, it's a good way to know if it's going from like -4 to 0 rather than from 0 to 4?
It depends on how you label your points.
Okay.
Okay, so if you can I copy a picture and then erase certain parts from it, but not the whole thing? On
Yeah.
Notability? Anybody know?
Yeah, you would have to be really delicate with the clipper tool.
Okay. All right, let's give this a try.
Or you might be able to color it with white. That might work.
Ooh.
Oh, wait, you can, yeah, if you do that, instead of click copy, you click duplicate, and then I think you can still erase individual parts of it.
Okay, well, let's try this. Oh yeah, okay, here we go. Okay, so let's say that you put your x-axis at the bottom here. And so when you label your points, you need to make sure that they label according to your diagram, right? So, so like the bottom points don't actually change. This is still 3, This is still 0. Oh no, sorry. The bottom points do change. This is going to be 2 and 0. This is going to be negative 2 and 0. Then this point up here will be 3, 4. This one will be negative 3, 4. So if that's what your diagram looks like, let's see if we can't set up an integral. So we know we still have the 62.5. We need to figure out the depth, and we still have our 1/2 y plus, well, I don't know. Let's make sure we still have that, okay? All right, so if we wanted to represent the depth here, what are people's thoughts on how we would represent that depth?
Is it just y?
0 plus y?
Yeah, we could do 0 plus y, right? The bottom plus whatever we're increasing it by, or that just gets us back to y, right? Because the depth of the water here is just going to be however tall that is.
All right, cool.
Okay. And then I think that it gets accounted for because now your bounds are going to be 0 to 4 because you're going up the y-axis. Okay. I don't know why it makes more sense for me to do these things upside down and like have more negative signs in there than I really should. So I apologize if that wasn't quite so clear for folks.
I appreciate that. Thank you.
All right, so we've got one last question here. Let's take a look at this last one. It'll give us just one more different cross section to keep in mind, okay? Now, one thing that you'll notice, for example, 3, like this 8 feet long part of the trough didn't even matter. Like we just wanted to see the force on the end, and so we didn't have to account for that 8 feet, okay? All right. We've got one last question. So we have a cylindrical oil storage tank that is 6 feet in diameter and 10 feet long is laying on its side. If the tank is half full of oil weighing 58 pounds per cubic foot, find the force exerted by the oil on one side of the tank. So in this case, instead of drawing a trapezoid as the end of the tank, we're going to draw a circle because that's the end of a cylindrical storage tank. So we will have a circle. Okay. Now, since we're dealing with a circle, immediately I'm thinking, which equation is the easiest to describe a circle? Because I know I'm going to need an equation at some point to describe the width. And to me, the easiest equation for a circle is you keep the center at the origin. So you don't even need like x minus anything or y plus anything. It's just x squared plus y squared. And then I just need to know the radius, and I need to square that. And so the radius in this case is not 6, but it's 3. So to me, this equation is the most straightforward way to describe this shape. And so because this is a little bit more complicated than like finding the slope of a line or whatnot, I'm going to center my coordinate axes at the center of the circle so that I can use the most simple equation possible. Okay. So that means that my vertical axis is along the x, or my vertical axis is right down the middle, but so is my horizontal axis. Okay. So this is kind of like the square one where we had the third scenario where we could have the coordinates at the center and then just kind of go like +2 and -2. It's kind of like that same idea, okay? So if we were to label a few coordinates here, I've got 3, 0, I've got -3, 0, 0, -3, and 0, 3. Okay. All right, so we've got our setup. Force equals pressure times area, which we know ultimately is going to give us density times depth times the width times dy. All right, so our density in this case, what is our density?
58.
Yeah, it is 58, okay? So the 62.5 is like, oh, it's water, and we're using feet. But if the whatever it is, liquid that we're submerging our plate into is not water, it should have a specific density, and that density should be given in the problem, okay? So this density is 58, okay? Now, as far as the depth goes, what do we want to describe as the depth?
Well, it's half.
It's half full. So that means that we've got the liquid in the bottom half of this.
Yeah.
Good catch, good catch. So how does that change our depth? So, Broy, I like what you have. We're going to use those for the bounds in a moment, but how do we describe the depth in the meantime?
Would it be 0 minus y again?
Yeah, it's going to be 0 minus y because we're starting here and we're going in this direction. So like a top minus bottom, okay? The width is going to be this whole distance across, right? How do we find that distance?
With the x squared plus y squared equals 3 squared.
Okay, and what are we going to solve for? Are we going to isolate x or are we going to isolate y?
X.
Yeah, we're going to isolate our x. So that will give me x squared equals 9 minus y squared, or x equals the square root of 9 minus y squared. And that gives us this half. But if we want the whole thing, we need a 2 times the square root of 9 minus y squared. Does that make sense?
I'm a little bit confused.
Okay, which part can I clarify for you?
So the 10 feet long, where did that go?
We're looking at just the force on the side of the tank. So we're not taking into account the 10.
So where do we know, like in the question, how do we know? Because for the first one, we did took it into account. So I guess I'm missing the information, like how do I know when I need to take it or not?
We didn't take it into account.
We did all the calculation with the 10 feet.
Right, the 10 feet is the depth, like how far it is under the water.
So in the example number 4 and example number 3,
yeah,
we didn't take it into account. We literally just did like either y or minus y.
We're only looking at the force exerted on like the end of the tank. The end of the tank is the circle.
Okay, all right.
Right? So yeah, sometimes there are going to be extra numbers in the problem, but with the 10 feet long, that actually doesn't tie into the force for like that side. Okay. All right. So I think from here, we're ready to set up our integral. And so someone had already said that our integral would have bounds from -3 to 0, right? Because we have the bottom of the tank is -3, we go all the way up to 0. And we have our 58 and 2, that's a constant. So I can go ahead and bump those to the front. So 58 times 2 is 116, but I'm also going to bring this -1 out. So I'll have -116 in the front. And then what I have left is y times the square root of 9 minus y squared. Okay. Now this is probably as bad as it gets in terms of the integral. And the only reason it's worse than the others because we have to use u sub here. But like, again, from the work that I've seen from you folks all semester, or all summer, the u sub is something that's coming pretty naturally to most of us. So it is a good skill, and I trust you guys to identify when you need to use the u sub, okay? So we'd have u equals 9 minus y squared, du equals -2y dy, or I have du divided by -2 equals y dy. All right. If you want to, you could also change your bounds here. So for example, u of 0, the top bound would become 9, because 9 minus 0 is 9. And my bottom bound, what would that be now?
Zero.
Zero.
It's going to be 0, right? So we just do 9 minus -3 squared, and we get 0. And so our integral that we end up taking is going to equal -116 over -2, because we have this -2 here. The integral from 0 to 9 of u to the 1/2 du. And that should give us 116 over 2 times, this is going to be u to the 3/2, so I have a coefficient of 2/3. I'm going to plug in 9, I'm going to plug in 0. All right, this 2 and that 2 reduce, which is really nice. So I have 116 over 3. And then to do 9 to the 3/2, that's the same as the square root of 9 cubed. And then I have to subtract 0. And so this gives me 116 over 3 times 3 times 3 times 3. One of those is going to go away. And I end up with if you change your bounds, then you don't need to put the y's back into the equation. So like this sort of bonus step right here, I changed my bounds, means I don't have to put the y's back into the equation. Okay, but you don't have to change the bounds, you can put the y's back in. All right. Okay, so this last piece down here, in general, I just wanted us to know that the force is going to be the integral of our density times our depth times our width times dy. Okay. And again, that comes from pressure times area, which we kind of spent a lot of time on for the first example, but the sort of bigger takeaway is at the end of the day, your integral consists of density times depth times width. And you just have to make sure that everything corresponds to the way that you set up your grid, okay? So example number 2 is probably a good one to go back and see like which one of these makes the most sense to you. But also knowing for like cases like example 4, I could make my bounds easier by putting the x-axis at the bottom, but it might make my equation writing harder, right? So it's a fine balance between the easiest way to write the equation and the easiest way to set up your XY grid. All right, so that brings us to the end of 6.8, which is the end of the content for tomorrow, all right? I know that there were a few questions, so I will stick around in case anybody has any questions, but I'm gonna stop sharing my screen and I'm gonna stop the video.